So this is the Maths 2021. I'm going to do questions 2, 3, 4, and 5 in this video, the longer form questions. I'm not going to do 6 and 7 just because they're more computer sciencey and that's not my area of expertise. Anyway, let's get into it. So this is question number 2. Let's start off. So it's all about log functions and their power series. We need to choose a value of x with mod x less than 1 such that we get this value here. Now it seems obvious to pick x as minus 1 because 1 minus minus 1 is 2, but we can't do that because minus 1 doesn't have a mod of less than 1. So you have to be a bit more clever, and also to give you a hint, all of these negative signs are going to have to change to positive somehow. So maybe you pick a negative value, or maybe you don't, maybe something else happens. It actually means you pick x as a half, and we'll see why this works in a second. Because when we put a half into here, we get log of 1 minus half, and we put a half into all of these x's. Now, I'm not actually going to expand this properly. 1 half squared is 1 squared over 2 squared, which is just 1 over 2 squared. But I can just shove the 2 squared onto the bottom here and not multiply it with this 2, and likewise this 2 cubed here and not multiply it, just because they haven't either. So that's what I'm going to do. 1 minus a half is a half. And now where do all these negatives go? Well, a half can be written as 2 to the power minus 1. And by power law for logs, we can move this minus 1 to here, and then we can times everything by minus 1. And we'll get the answer as required. Okay, so that's the first bit done. And now we have this fact, which they've told us, which seems really cool, but is actually not very interesting at all. All it's saying is, when n is bigger or equal to 4, this fraction is less than this one, which is obvious because all you're doing is dividing by a bigger number than you were before. So if you change this to a 5, this fraction is smaller, a 6, this fraction is smaller, just because you're dividing by a bigger number and everything else is the same. Now, how is this going to be helpful to us? Well, I need to bound this thing above and below. So what I'm going to do is I'm going to use this thing first, and I'm going to say, okay, what if we just replace all of these fractions with 3's instead? So change that to a 4 to a 3, that 5 to a 3, the 6 that comes next to a 3. If I did that, all of these fractions would become bigger. And so therefore, this entire side would also become bigger, and I end up with this inequality, where this side is now bigger than what this thing was. And all of these are just going to get changed to 3's. Now, how is this good? Well, I can just evaluate this bit, and here I can factorize out a third from everything. And this is just a geometric series that I can add up, because its common ratio is a half, times this by a half to get to that, because the power of 2 just increases by 1. And I can sum up an infinite geometric series where r is less than 1, like this, or mod r, I guess, is less than 1. First time is an eighth. Sort this out and you get a quarter, put a quarter into there, times it by a third, get this, add these things together, eventually you get this, which looks good. Looks like that's what they wanted me to. So that's bounded from above. What about bounded from below? Well, this is actually easier to do, because all you have to do is just ignore terms, right? This is log base 2. If I just straight up ignore these terms here and everything that comes after them, then this entire side will become smaller, because I'm just ignoring adding things that I should have added. So this whole side becomes smaller, and therefore log 2 is now bigger than it, if I just ignore all of this. But of course I can just evaluate all of these, and then add them together, and I'll get this, which is conveniently exactly of the right form. So k is 16, and I get this bound. So next it wants me to sort out log 3 over 2. Now this is easier because 1 minus x equals 3 over 2. I can just use x as minus a half, because 1 minus minus a half is 3 over 2. So I just shove minus a half into this, and now anything to an even power becomes positive, but there's still a negative there, so that will become negative. Anything to an odd power is negative, but with this negative will become positive. So the odd ones will be positives and the even ones will be negatives. And the trick with these 2's is the same as it was before. And now, okay, what can I do here? Well, I can break log of 3 over 2 into log of 3 minus log of 2, just by log laws. Which is helpful because now I have a power series for this, I have a power series for that, and I can just have that one in the middle, and I can rearrange these to give me a power series for log 3. Now when I expand out this minus here, this will cancel with this, and this will cancel with this. So all the even things cancel. I can add a half to both sides to make this into a 1, and add this to both sides to get 2 lots of these, add this to both sides to get 2 lots of those, and so on. So I have 2 lots of all of the odd things. But of course this 2 can cancel with one of these 2's to leave a 2 squared on the bottom. This 2 can cancel with one of these 2's to leave a 2 to the 4 on the bottom, and I end up with this kind of thing, which will just go on forever, as we know. So good, we have that as well. And now, this is a very common thing in maths, for them to essentially tell me to do everything that I just did all in one go. So previously it walked me through how to bound log 2 between 2 things here, but now it's not going to. Now it just expects me to have learnt that, and can now just do it myself without any prompting. So okay, I've got this series for log 3, and I want to bound log 3 from above like this. So do the same trick we did before, whereby we find some trick like this, where we say, okay, let's just replace these with something smaller, and then we'll make all of these fractions bigger. So let's replace all of these with 3's. I'll just replace all of these with 3's, and make all of these fractions bigger, so this side is bigger. And now I can factorize out a third from this side, just like I did before. This is a geometric series, this time with ratio 1 over 2 squared. First term 1 over 4. 1 over 2 squared is a quarter, of course. Sort that out, put it in there, and you don't get the right bound, which is disappointing. But that's okay, and in these longer form math questions, that often happens, right? You just have to do the wrong thing first, so that you can then definitely do the right thing afterwards. And I think what I established here was my mistake, was look at this 10 here. How are you getting a denominator of 10? Well, 10 is made out of 2 and 5, right? So I must have a 5 somewhere in the denominators to make this, which I got rid of here, right? I got rid of this 5 and just made it a 3. So my deduction here was that I need to keep this 5, and I instead need to change all of these odd powers beyond these to a 5. So now I'm going to keep this, and make all of these 5's. So every number after this, the 7 and the 9 and so on, make them all 5's. And just do the same thing again. Evaluate this, take out a fifth from all of this. This is now the same, it's a geometric series just like it was before, first time 1 over 16. Sort that out, put it into here, times these things together, sort them out, and you eventually get the right bound, which is good. So sometimes you just have to make a mistake to get things right. And now, of course, bounding from below is a bit easier, because all I have to do is ignore a bunch of terms. In fact, I think I can just ignore all of these and just have these two, and say log 3 is definitely bigger than just these two. Sort those out, and you end up with the right bound as well. And so now we have a good bound below and above. And now, final bit of the question, which is larger, this or this? Well, if we're establishing which is larger between these two, the whole question has been about logs, right? So surely logs have to do with this part of the question as well, except they don't immediately look like they are. But the thing about logs is they're increasing functions, right? Like they look like what my mouse is doing right now. They just strictly increase. So whichever one is bigger than of these two, their log is also bigger than the other one. So I can just compare the logs of each of these. But of course, by taking log of this 17 can bounce to the front, and now I have log 3, which I already bound between two things. So this thing here is between this and this. 17 lots of this, and 17 lots of that. All right, and I can work these things out if I want to, though it turns out to be unnecessary, as you'll see. And now, of course, again, take log of that, and move 13 here. I don't have a series for log of 4, but 4 is just 2 squared. Put the 2 over here as well, and now I can bound this between these two things here. And what I notice here is, if I say this is 2 times 13 and this is 2 times 12, I can cancel the 2's to get this. But this thing here is the same as this thing here, right? Because 17 times 13 is the same as 13 times 17. So if this thing is less than this, and this thing is more than that, then I can just write this thing here, and say this thing must be more than that. And so this is the larger one. Good, and that's all of question 2 done, so we'll move on to question 3 nice and quickly. It's all about polynomials. Let's do this. So we have a polynomial with turning point 0, 0. Explain why this and this. I mean, this is just fairly trivial and obvious, right? If it has a turning point at 0, 0, that means it goes through 0, 0. So if the function is y equals p of x, for example, y and x is 0 at the same time, so you just get 0 equals p of 0, I guess. Okay, fine. And this as well. Well, by definition of derivatives, if you differentiate this and it has a turning point at x equals 0, then p dash of 0 is 0 at that point. So again, I'm not really sure what they were expecting me to say there. Anyway, explain why there is a polynomial such that this happens. Well, again, this is basically what we just said, right? If it goes through 0, 0, then that means that x minus 0 is a factor, right? If it has a root at 0, then x minus 0 is a factor. That's just factor theorem. If p of 0 is 0, then it has a factor of x minus 0. But from graph sketching in chapter 4 of year 12, you learn that if it's got a turning point there, and it just touches the axis at 0, 0, then it's a repeated root, then it's x minus 0 squared, right? And of course, this is just a way of writing x squared. And so we have our answer here. Essentially, what they want to say is when you differentiate this, you get 2x, which of course means when you put 0 in, you still get 0 times something else, because x is still just 0, which means this is satisfied. I'm not really sure what they're asking for, to be honest. Anyway, polynomial r of x has a turning point a0. Now, all that means is that it's this polynomial shifted a to the side, right? So we can just write this and just shift it a to the side like this. And that's the way that we write that. Easy. Good. So now we have a polynomial that's degree 4, so its highest power is 4, and it has turning points here and here. Now we just decided that if a polynomial has turning point a0, then it has this as a factor, x minus a squared. So if it has one here and here, it has both x minus a squared and x plus a squared as factors. But if it has both of these things, well, these sum up to 4, right, when you expand them out. And so it must just be those things. There can't be another x, because that would make x to the 5, which we don't have. Of course, there's a slightly more general way of writing this, which is to just shove a constant in front. So I think that's it. I don't understand what justify your answer meant, so I just put a picture of this on the screen, and then, okay, sure. Describe the symmetry of the graph. Well, if we draw this, we have turning points at a and minus a, and it's a quartic, so it starts up here and turns up here. I think it must look like this, and I know it must look like this because I've drawn graphs like this all the time. Now, I'm suggesting it has a turning point at 0 here, which I'll just very quickly prove, because we can just break out this squared into here, because you distribute this square. Otherwise, multiply these two things together, square this out if you want to. This bracket should end there. I just didn't type it properly, but it doesn't really matter. And then when you differentiate this, this goes away. This becomes 4a squared x. But of course, when you put in 0 to this, you get 0. So this definitely has a turning point at 0. So I think I've done this in the wrong order, but it definitely has a turning point at 0. So the x-coordinate is 0 for its second turning point. But that's also interesting because it means it has a line of symmetry on the y-axis, which I can prove because if something has symmetry around the y-axis, then that means that it's an even function, which means f of x equals f of minus x. So essentially, if I take f of x, which is this, and replace all the x's with minuses, those two things should still equal each other, is what I'm claiming here. And I can prove it because the negative squared equals a positive squared, so like minus 5 squared is equal to 5 squared. So I can just replace this with x plus a, because a negative squared is the same thing its positive counterpart does. And here, I've just written these the other way around. But again, 5 minus 3 squared is the same as 3 minus 5 squared, right? Because subtraction isn't commutative, but it does at least create this something of the same modulus value, right? 5 minus 3 and 3 minus 5 are both 2, just one is plus, one is minus. So when you square those end up being the same. So this is the same as x minus a squared, which is exactly what's written here. So it does have symmetry around the y-axis, and I've just proved that algebraically with some explanation, and I've already answered this at x equals 0. So that's all of that done. Is there a polynomial of degree 4 which has turning points here, here, and here? So if we sketch this, we have turning point 0, 0, 2, 0, and in the middle here, 1, 3. Now, it seems very obvious that this does exist because of the drawing that I just did, this one here, where I said there was symmetry here and this and this. But here, this turning point is in the middle of these two things, right? This is 0, 1, so this x-coordinate is 1. So it's bang in the middle of 0 and 2. So I think I can make this graph just by graph transformating the other one. I can't be bothered to write down exactly what those transformations are, but I can surely just shift the graph to the right a little bit and then flatten it down or stretch it out, depending on whether this is higher or lower than the other one was. And I can surely get this. I think that would be enough just saying that. You could also prove it algebraically. You've got a turning point at 0, 0, so you must have this as from the first part. But you must also have this because it's got a turning point at 2, 0. So this is the entire polynomial. You can check that this goes through 1, 3 by putting in 3 here and 1 here. You find k is 3, so you have this polynomial, which I've expanded out a little bit. You could differentiate it if you wanted to, and just check that the derivative is 0 when x is 1, because this needs to be a turning point, remember. So check the derivative of 0 when x is 1, and it is. So this sort of makes 0, so good. So this is fine, this exists, which I think just said there. Anyway, does this exist? So again, let's just quickly sketch it. 1, 6, 2, 3. Sorry, this is 4, 6, isn't it? Because it's the same height. And then 2, 3. Now notice how 2, 3 isn't in the middle of the other two. And this is a problem because essentially we proved in the other part with this picture and with some algebra that if you've got roots at a and minus a, then the symmetry is in the middle of them. And now I know that we haven't got roots here on here, but surely we can just, again, take whatever whatever quartic this is supposed to be, graph transformate it until it has its roots looking a bit like this. And then because this turning point isn't in the middle, because like any graph transformation would keep this turning point where it is relative to the other two, wouldn't it? If you just translated it around, shifted it down a bit. But it can't be because it's not in the middle of the two. So yeah, this doesn't exist. Cool. That was my justification. This is quite a nice question here. It's about cutting a square cake, because apparently context is important in maths. So What's the area of this slice in terms of x, k, and y? Well, I did year 8 maths, so I know if this is k, this is y, and this is x. The area of a trapezium is half y plus k times x. So yeah, sure, I can do that. I can verify it as well because I can substitute 1 into things. Cool. Find another point such that choosing k as 1, that gives me an area of 1. Okay, so I'm going to choose k to be 1. Let's just pretend this is the point 0, 1. And I want an area of 1. Now, I just noticed that if you just make a triangle, this whole area is 4, so I want a quarter of this whole square. So if you just make the slice go down to there, this is a quarter of the whole square, isn't it? Because this is half of it, half that to make a quarter of it. So if you just choose the point 2, 0, you're going to get that. There are lots of other places you can pick. Show that it's possible to choose a value of k that gives a slice if both this and this. Okay, so we have an area of 1. So this is the formula for the area, and that equals 1. We can expand that out if we want to, and we can double everything because I noticed there are 2's here. And now kx and y are all positive numbers, right? It says so here. Cool. Which means that xy, this is positive, but it could be very small. But xy has to be less than 2 or equal to 2. Because you can choose k to be 0, I believe. So we can just say that because this is positive, this has got to be less than or equal to 2 to make this work. But likewise, we could take this whole thing here, again, and we could say, okay, well, k is less than or equal to 2, right? So if you just replace k with a 2, and I didn't really know to do this, but I just noticed if you doubled this, it looks a lot like this, just with a k here instead of a 2. So if you just, so I just thought, okay, well, what it wants me to do is if you replace k with 2, this whole thing becomes bigger, or equal, I guess. So we can say if this becomes a 2, we have a bigger than or equals to sign here, which is exactly what they wanted me to get. So I kind of reverse engineered that one. I was like, well, they want me to have this. I have this. Just replace this with this and change the sign. Good, justify it. Okay. So sometimes they help you out by giving you the things that you need in the first part of questions. You don't have to work it all out on your own. Sketch the region R for which both of these hold. So I need to rearrange these in terms of y so that I can sketch them. And again, x and y are only positive, so I'm only interested in drawing a graph up this area. Now, the graph of 2 over x, we should know looks like this, roughly, I guess. There's no scale here, so I think I'm okay to draw it like this. This one rearranges to be, it's a little bit harder to rearrange, but it becomes this. Now, this is just this graph translated down, isn't it? So it's just shifted down 2 places, so it becomes that. Now, indicating any relevant points on the edges of the cake. It took me a while to work out what that meant, but of course this graph not only is bounded in the top quadrant because x and y are positive, but also they're bounded by 2 and 2, right? They can't be bigger than 2. So let's bound these at 2 and 2, and then let's just talk about what all these intersections are. I think that's what it means, relevant points on the, we imagine this is the cake, and on the edge of the cake they just want us to tell them what the points are. So this is the black curve, which is this one here, when y is 2. So 2 equals, just pretending because we're on the curve, it's equals. 2 equals 2 over 1, I believe. So this is the point 1, 2. And likewise here, this is when x is 2. So 2 over 2 is 1, so that's going to be 2, 1. This one here, I think I did next apparently. So that's when y is 2 on this curve. So you put that 2 there, add 2 to get 4. Then 2 over 4 is a half. So we're going to have this. And then this one was 2, 1, as I said. And then this one is when y is 0 in the red curve. So you put 0 here, you add 2, and you get 2 over 1 is 2. So that's going to be 0, 1. No, it's not. It's going to be 1, 0. Apologies. I'm just going to very quickly fix that because it's made me very unhappy. This is 1, 0. Good. And I think those are all the points on our relevant cake, which means that essentially all this is saying is that this cake, to have an area of 1, you need to put x and y somewhere in this region here, which I probably should have colored in, but I just couldn't be bothered. But you need to select it somewhere here, and then if you do so, there'll always be a k value you can choose to make area 1. So for example, we cut it earlier, I think 1, 1, didn't we? And the k value was just 1, and that gave you an area of 1. But also you could make k1 and cut it here to make area 1, and likewise there are a bunch of other places you could cut it. Good. And again, this is a bit like the previous question we did, where it's going to give you a different situation. This time he's cutting up at the top edge, and they just want you to do the entire thing in one go. So they want you to take everything that you learned in the previous 4 bits and just do it in one go. So we draw the graph, we say, okay, what's the area of this? Well, we need to split into two because it's not a trapezium, it's a pentagon actually. So split into, this area is xy, this area is a trapezium, this is 2 minus y, because that's 2, that's y. This is m, this is x. So the area of that is m plus x times a half times this. So the total area, if we want it to equal 1, is this plus this equals 1. And now we do a similar thing that we double everything. And a very similar thing to what we were doing before, right? You say m is less than or equal to 2, because you can cut it anywhere along here up to 2. If you just replace it with 2, this entire side becomes bigger, or equal to. So we end up with this, which we can expand out and simplify if we want to, and we eventually end up with this. And then from the other side, you do the same similar kind of thing. You say, well, m is bigger than 0, so if I just replace that with a 0, this whole thing becomes smaller than or equal to. And then we get this, which we can simplify out to this. And now it's a case of sketching these two things. Now to sketch these two things, we want to rearrange them both for y, probably, to get this. Now be very careful here. It didn't really matter, and I'll explain why later. But when you divide this by x minus 2, this inequality flips, because x is less than 2, so this thing is negative. So the inequality flips when you divide it by. And then I didn't really like this, so I just times this by minus 1 over minus 1, which doesn't involve flipping this, because you're times by minus 1 over minus 1, you just times by 1, just to make it look a bit better. Here's a bit more straightforward. You just factorize out an x, divide it. No, you don't. You take away 2x, then you divide by x, and you get this. Okay, and that's all fine. Okay, now let's sketch it. So again, and it's tempting to think these two are very complicated to sketch, but actually all you really need to do is say, okay, well, when x is 0, where is y on this? When x is 0, you get 2 over 2, so y is 1. So that's not too complicated. And likewise, when y is 2, just to find the other edge bit, when y is 2, you can solve this in your head if you want to, but eventually you get x as a half. And you also notice when x is 2, this is going to be divided by 0. So this is some kind of curve that asymptotes up to infinity when x is 2. So it's going to look a bit like this. I'm just not bothering to draw it beyond the bits that I need. And then something very similar to this. So well, when x is 0, it immediately asymptotes. So it doesn't actually hit here. It sort of asymptotes up to infinity there. So let's ask when y is 2. When y is 2, you get 2x equals this thing here. Add 2x, divide by 2, you get a half. So it goes through the same place. And then when x is, then I asked when y was 0. I thought maybe that's something. Oh yeah, when y is 0, you just need this thing to be 0. So x is equal to 1. So it goes through 0, 1. No, it doesn't. It goes through 1, 0. Did I change that to the wrong thing in the? Or, I don't know. I can't remember. Anyway, so it goes through 1, 0, and again it asymptotes up to infinity here, so it looks a bit like this. And you need to be below the black and below the red. This is where the whole. I didn't notice when I divided this by this the first time to change this, but then I got this thing being bigger than this, and it was looking like it had to be above this and below this, which didn't make any sense. So that's when I noticed the mistake. But you need to be in this region here, and that's the entire question done. Good. So we're at the last question now. I think this is probably the most tricky one of all of them, actually, on this paper, at least up to question 5. You're talking about triangular triples. Essentially, this is introducing you to an idea called the triangle inequality, where if you have a side of a triangle like 3, the other sides can't be 1 and 2, because if you try and draw a side length of 2, like out this way, the 1 won't reach this point here, and you kind of intuitively know that, because 2 plus 1 is 3, so to have these two lengths have any chance of getting from this corner to this corner, they just have to run along the entire length, because they add up to 3 themselves. So the moment that you kink them out this way, they're not going to reach the end. So this is called the triangle inequality. It just means that the two smaller sides of the triangle have to add up to something more than the bigger side, because as you sort of kink them out and make them go further away, they have to be greater to compensate and get back to the final point. So that's just what the triangle inequality says, and it's saying how many of these are there for certain perimeters. So okay, how many triangles have perimeter 3 that actually exist? Well, only one of them does, the 1, 1, 1 triangle, because it's just an equilateral triangle length 1. You can't have a side length 0, and these all need to be positive integers apparently. F of 4, there are actually no triangles that do that, because you can't do 1, 1, 2, because for similar reasons to this, if this was length 2, 1 and 1 wouldn't be able to reach it the moment they went out anywhere. So that has 0. You can't do anything else because you can't make side length 0. F of 5 you can do 1, 2, 2, and then apparently it counts just a rearrangement of the numbers for some reason. So okay, we'll just do that. So there are 3 of those. And then f of 6, there's only one off, just the equilateral triangle. Again, you can't reduce this down to a 1 and increase this to a 3, because then you're just in this situation. So there's only one of those. So that doesn't actually exist, that doesn't work. Okay, so that's the first bit. If ABC is a triangular triple, show that this is also one. Well, if it's a triangular triple, there are two things you need. You need them to be positive integers, but if A, B, and C are integers, because this is a triangular triple, then A plus 1, B plus 1, C plus 1 are also integers. So it passes the first test. It also needs A plus B to be greater than C, where A and B are the smaller sides, as I explained here with this picture. But of course, if this is true and you add 1 to everything, you've added 2 to the bigger side and 1 to the smaller side, so the bigger side is definitely still bigger. So that's that done. 2. If it's got an even, what is this? If the perimeter is even and bigger than or equal to 6, show that the sides are at least 2, and this is also a triangular triple. So showing the sides as at least 2 is quite easy, because if you make one of the sides 1, and it's got an even perimeter, then y plus z are definitely odd, which means they differ by 1. One is odd and one is even, right? Because to make an odd, you must do odd plus even or even plus odd. But if one of them is odd and one of them is even, that means they have at least a difference of 1, like 6 and 7, or 5 and 6, or 10 and 11. But if their difference is 1, you can't have your last side be 1, because then they'll at best add up to the biggest side, just like this picture does here. So the difference is not bigger than the third side, which means you don't satisfy this inequality here. So I hope you know what I mean by that. Okay, last bit. If you take away 1 from every side, show that that's also a triangular triple. Well, okay, so take away 1 from every side, you get this, assuming that this is holding, which we know it does. Now, you get, okay, so you minus 2 and then add 2 to both sides. So we're looking for this to be true, essentially, for this to still be a triangular triple. Now, okay, we know this is holding because we know x, y, z is a triangular triple. Now what we can do is we can say, okay, well, because everything's an integer here, if this is bigger than this, then at worst it's only 1 bigger. So if we just add 1 to this side here on the right, this is bigger than or equal to. Because worst case scenario, this could be like 5 bigger than this, in which case this is still just bigger. But if it's only 1 bigger, then it's now equal to. But it's definitely not going to be less than, because these are integers. So at worst, this is 1 bigger than that. Now the thing is, if we just assess the case, now what I want to kind of show is that it's still not equal to, because if I just showed that this wasn't equal to, then I know this would be true, because this is just this without the equal sign. And if this is true, then I've got what I want to do. So let's show that this can't actually be equal to this. And there's a really nice trick here, which is just add z to both sides. And now this is the perimeter, but the perimeter is said to be even. But this is an integer, and 2 times an integer plus 1 is odd. So we have an even equal to an odd. So that can't be the case. So actually, this can't be equal to this, which means that it's bigger than, which means this is true, which means this is true, and which means this is a triangular triple. That was quite a hard proof, I thought. But anyway, we're right up to the end of the question here. We've done this, we've done that. Use the previous 2 parts, prove this. Now, okay, if f of 2k equals n, say, so k is just a number, f of 2k is, so this is the number of triangular triples with a perimeter this. We've just decided that if you add 1, or it says here, if you add 1 to every side, you also get a triangular triple. But also if you take away 1 from every side, you also get a triangular triple. If the perimeter is even, that is, which it is because I've written it as 2k. But if you take away 1 from every side, you decrease the perimeter by 3. So that means that I decrease this perimeter by 3 to make 2k minus 3, but n stays the same because all of the previous triangular triples are still triangular triples. And what I'm saying is it's at least n. It could be more, I guess, because although all of these n have a corresponding this solution in here, it could be that this number here has other triangular triples that don't match with the ones you originally had. That sounds a bit confusing, doesn't it? But essentially, imagine all of these solutions are turning into new solutions when you take 1 away from all the sides. Sure, that gives you at least n solutions in here. There could be other things in here that just exist on their own and don't have anything to do with this, except there aren't, because if you start with this and you add 1 to every side, you definitely get a triangular triple every time. But if you add 1 to every side, the perimeter increases by 3. And so what this means is you have this 1-to-1 back and forth correspondence where everything in here, when you decrease 1, every side by 1 becomes something in here, and everything in here, when you increase every side by 1, becomes something in here. So there aren't any weird triangular triples that don't have anything to do with the other one, because all of the ones in here decrease by every 1 to make everything in here, and all the ones in here increase by 1 to make everything in here. So there's this 1-to-1 correspondence, and so this does actually equal this, right? You can turn 1 from the lower section into the upper, and so on. I hope I've explained that okay, but I don't know whether I have, to be honest. Okay, very last bit now. We'll consider the case where the perimeter is even, and we'll write this. Okay, show that in the case A, B, and C, the triangular triple this, if and only if all of the sides are strictly smaller than S. Okay, so the perimeter is 2S, and what it wants me to show is that all of the sides are definitely less than S. Now this makes a lot of sense if you think about this geometrically, because if you've got a perimeter of 2S and one of the sides is more than half of that, think about trying to join up the triangle. You're not going to be able to do that because the other two sides are going to be less than the third one. But let's just prove that algebraically. So if A is the biggest side, and you can repeat this with B and C if you want to, and A is bigger than S, so we're doing this by contradiction, and A is bigger than S, then we can say that this, replace A with S, and this side becomes smaller. Right, because A is bigger than S, so if we replace this side with S, we've made this side smaller. But of course this doesn't work, because when you take away S from both sides, you get B plus C is less than S, which is less than A. And that doesn't work for triangular triple. The whole point of triangular triples is the two smaller sides add up to something bigger than the biggest. And you can repeat this argument with the other two sides, and you'll get the argument here, the required. Okay, for any A such that A is less than S or equal to S minus 1, which we just decided is the biggest it could be, show that the number of values of B is this. Okay, so this is the hardest bit of the question, I think. But what we can say is C equals this, so P is just replaced with 2S. Now, C is less than this, because the argument that we just made for A being less than S minus 1 or equal to is the same for the other two sides as well, right? So, okay, and again, we'll do the same kind of trick. There's lots of inequality stuff in this paper, isn't there? Where you replace C with this thing, therefore making this side bigger, because you've replaced it with something bigger or equal to, so the entire side becomes bigger or equal to. But now, of course, you can sort this out, and you get this if you rearrange for B. And so we've got B is bigger than this. But likewise, C is less than this, A is less than this or equal to, also B is. Right, because this rule applied to all of the sides, remember. So now we've trapped B in between two things, and now we can say, okay, well, how many things are there in between the two? Because that's how many values B can take. And be super careful with this, because if B is trapped between these two values, say, with these inequalities, then B can be 7, 8, 9, or 10. It can be 4 values. So I was really tempted, and I did just do this minus this to find out how many B's there were. But that gives you 1 less, right? 7 minus 10 is 3. So then, but there are 4 things this can be. So just add 1 on the end, and you get the answer required. Again, they helped me out here, because if I didn't have this, I would have just said it was this minus this and got A minus 2. But I just had this. I thought, how have I gone wrong? Get out a numerical example, check it, and that was my mistake. Add 1, and you get this here. Okay, so hence find an expression for f of p, the number of triangles for perimeter p, the triangular triples, for any even p greater than 6. So okay, what we've decided here is for any a value, and a can be anything from 2 all the way to s minus 1. Yeah, s minus 1. B, for each given a value, b can have a minus 1 options. So if a is 2, b has 1 option to b. It can only be 2. We've already decided the side lengths can't be 1. If a is 3, b has 2 options, right? 3 minus 1 is 2 options. It can be 3 or 2. If a is 4, b has 3 options, and so on, all the way down to here. And so adding up all of these is the number of triangular triples you can have, right? Because we've just laid it out. We said if a is that, if a is that, is a is that, and so on. This is the number of choices you have for each one. So we just need to add up all of these to get the number of total triangles we can have. And of course, adding up consecutive numbers from 1 up to some number is just n. If the number is n, it's n into n plus 1 over 2. You've probably seen that before. So here we just need to say the number is s minus 2 times s minus 1, which is the one bigger than it, divided by 2. And that's our formula for the number of triangles that we can have. So finding f of 21 then, it's the formula again. Now, from the previous part, we decided that f of 2k minus 3 is equal to f of 2k. So f of 2s minus 3 is equal to f of 2s minus 3, which means that f of 21 is the same as f of 24, if we just make s 12 in this case. So okay, instead of looking for 21, we'll look for 24. We can just, but of course this is a formula if we've got an even number of perimeter. So we can just use s is 12 in this formula, and we'll get the answer of 55. And that's the entire paper done. Thank you so much for watching, and I'll see you next time.